pouco da transmissão. Ok? Então, já estou aqui no YouTube, está preparando para dar, configurando a reunião. Quando estiver aparecendo para vocês aí, transmissão ao vivo, vocês me avisem. Apareceu?
Ainda não.
Acho que está aí, sim.
Sim, apareceu no meu aqui que está transmitindo no YouTube.
Live no YouTube. Apareceu live. Mas eu estou no YouTube e não acontece nada, não vejo nada lá.
Ah, você não precisa ver, cara.
É um delay, tem um delay.
Não. É só para saber se está mesmo lá, se eu estou aparecendo bem, bonito, não sei. Não, é que tem muita gente que está interessada em assistir.
Olha só, pessoal, estou todo mundo me ouvindo?
Estou vendo.
Sim.
Então, Hélio,
eu também, tudo bem.
Você pode dar início, então, à defesa de tese do Jean. Ok?
Okay. Hi, good afternoon, everybody. We are here for the thesis presentation of Jean Cáceres Vera. And I will ask everybody to turn the camera off. And the way it works was explained by Ricardo. And the only thing I have to say is that in case there is the connection drops for whatever reason, we just restart from where it stopped. Okay, but we hope nothing will happen. And so at the end, then there will be the questions. I ask the members of the committee to restrain the questioning for after the presentation, unless there is something very, 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 very serious. And then we go to the presentation. After the presentation, then we go for a private convening. Any question for the members of the committee? Now, let me introduce the members of the committee. Today, we have, for the defense of Jean Cáceres Vera, Dr. Jorge Morfin from Fermilab. We have Dr. Ana Amélia Machado from Unicamp. We have Dr. Gilvan Alves from CBPF. We have Dr. Carsten Hensel from CBPF. And we also have Dr. J. Anjos from the National Observatory and CBPF. And myself, that will preside on the session. Okay, so this is being transmitted live on YouTube. And Jean, you have 50 minutes for your presentation. I ask you to start sharing your screen and please get full screen. And you have 50 minutes. After this 50 minutes, then we go for the talks. Okay, Jean, it's up to you now.
Okay, thank you for the presentation. Can you see my screen?
Yes, but it's not full screen.
Not full screen.
Not full screen. I'm going to stop sharing. I'm going to share again.
It has the thumbnail on the left side.
Yeah. Try Control F
okay.
or something like that. Control F, Shift F.
Yeah. So I have it here in full screen, but let me try another file that I have ready. Okay. What about now?
Yes, okay.
Much better.
Just a moment. Ricardo, eu não consigo ver nada no YouTube. O pessoal, é só entrar no YouTube, não aparece nada lá.
Já está ativado, tá? Já tem 9 pessoas assistindo.
Ah, é? Eu não vejo nada. Bom, enfim, tudo bem, vamos em frente.
Entra lá. Você está inscrito no COEDU?
Não, tem que estar inscrito?
Você vai lá, se inscreve lá na COEDU, naquele endereço que eu passei por e-mail. Acessa lá, já está no ar. Já tem pessoas lá, tá bom?
Ok. Jean, you may start.
Okay. Okay, thank you for the presentation. Okay, so my name is Jean Cáceres. I am a PhD student at the Brazilian Center for Research in Physics. And I have developed my doctoral analysis at the MINERVA Experiment. So today I'm going to present you my analysis, and my analysis is the measurement of neutrino cross-sections interactions in the shallow inelastic scattering region in hydrocarbon at an average neutrino energy of 6 GeV in the MINERVA experiment. Okay, so this is a broad outline of what I'm going to present. I'm gonna give a brief introduction of neutrinos. Then I'm going to talk about the MINERVA experiment, the detector characteristics, and the reconstruction. And finally, I'm gonna report my results of my analysis. Okay, so first of all, let me talk about the standard model. We know the standard model is the mathematical model of elementary particles and fundamental forces that is very highly successful in describing experimental results. All quarks and leptons have an antiparticle. This means that they have an identical mass with opposite quantum numbers. Particles interact by exchanging a force carrier particle, and a standard model can describe three of the four forces in nature: electromagnetic via photons, strong via gluons, and weak via bosons W and Z. And unfortunately, it doesn't describe gravity. So neutrinos in the standard model are three. They come in three flavors. They are electrically neutral. They only interact by weak force. And this is important. Neutrinos are massless in the standard model. Each neutrino also has a charged lepton partner. And here I'm showing you a couple of examples for a charged current event and a neutral current event. So in a charged current event, the incoming muon antineutrino exchanges a W boson, and the outcoming particle is a muon positive. For the neutral current, the particle exchange is a Z boson, and the ingoing neutrino is the same as the outcoming. So neutrinos oscillates, and this is a quantum mechanical phenomenon in which a neutrino with a specific flavor is measured in a different one. So neutrino oscillation is possible just if neutrinos have non-zero masses. We can describe a state of a neutrino by a superposition of mass eigenstates, nu1, nu2, nu3. The relation between these eigenstates with the state of the neutrino is made by the terms in the MNS matrix, which each one represents the probability of measuring a neutrino with a specific mass. Simplifying these three flavor system, we can find easily the terms of the probability for two flavors that are cosinusoidal and sinusoidal. When we extract the probability of oscillation, we can see that the probability of oscillation depends on a theta angle. The difference of the masses of the neutrinos, the length that the neutrino traveled, and the energy of the neutrino. So these are called the oscillation parameters, the theta angle and the mass of the neutrino. So for this reason, measurement of neutrino properties, especially oscillation parameters, will provide a physical information beyond the standard model. MINERVA studies neutrinos. So what is MINERVA? It's a dedicated neutrino scattering experiment in the NUMMI beamline at Fermilab. The main goals are to understand the nature of neutrino-nucleus interaction by identifying the nuclear effects and testing the models that the generators use. We also measure exclusive and inclusive final states and the correlation of those with leptons. Other goal is to characterize neutrino interactions for oscillation experiments. So these are the main channels measured in MINERVA for our specific beam, our beam of neutrino muon. For quasi-elastic scattering, the products would be a muon negative and a proton. For pion production, we have the corresponding lepton produced, the muon negative, and the nucleon and pion plus or pion zero. In deep inelastic scattering, where quark fragmentation is involved, we recognize muon negative and a shower of hadrons. Each of these interactions happens in a different region of the neutrino energy. from quasi-elastics for low energy to DIS for higher energy. Okay, so first, how is the beam produced? To produce the beam, first, we collide the 120 GeV protons into a graphite target. This collision produces pions and kaons that are going to be focused using a magnetic horn. This charged particle enter the decay pipe, where they have enough length to decay. They decay in muon plus or a muon neutrino. So basically, this is how the flux of the muons of the neutrinos is produced. These products are later going through an absorber of remaining hadrons and muon monitors to tag the muons. This is a broad view of the MINERVA detector and the main components. The MINERVA detector is mainly composed of an active tracker region that is just made of scintillator material. Upstream the region, we have the nuclear target region that have different nuclei: carbon, lead, iron, and water. And in addition, we have liquid helium in a cryogenic container. Also, we have the electromagnetic calorimeter in the yellow area. The cyan area is the represented the hadronic calorimeter. Downstream the MINERVA detector, we have, when we use the MINOS detector as a muon spectrometer. We use this to measure the momentum of the muon of a charge current interaction in MINERVA. So the core of the detector, the core of the detection would be the scintillating light. We use triangular plastic scintillator strips arranged one next to another one. And to this arrangement gives a better position resolution. We achieve a spatial resolution of 3 millimeters and a timing resolution of 3 nanoseconds. In addition to this, the planes that are formed with this arrangement of the strips are also rotated 60 degrees respect to the vertical. This will allow a 3D reconstruction of a particle going through the planes. Each of the planes is composed of 127 plastic scintillator strips. So the fluorescing light is absorbed in a wavelength shifting fiber. You can see the wavelength shifting fiber here in this plot that goes through the scintillator strip, contains the light via total internal reflection. This goes through a clear optical fiber into a photomultiplier and then to the readout. So what do we see in the detector is basically the position of energy. Here I am showing you a couple of candidates, event candidates for pion production and muon neutrino quasi-elastic. So for pion production, we recognize 3 tracks, and the lone track is identified as the muon negative. This goes through MINERVA, loses little energy, and tend to exit the back of the MINERVA and reach MINOS. The other 2 short tracks could be the pion and the plus, the pion and the proton, but we would need the energy deposition profile to identify which one is. And down, we have a candidate for the muon neutrino quasi-elastic, in which there are just 2 tracks. The lone track identified as the muon negative and the proton as a short track. So as a summary, the event reconstruction is made of two parts: the reconstruction of the muon and the reconstruction of the particles produced that are not muon. So here I'm showing you the muon that is produced in the tracker, goes through MINERVA, and then is reconstructed in MINOS. And the rest of the particles will be reconstructed by the calorimeters and the scintillator strips in MINERVA. So let me talk to you about how we do the reconstruction of the hadronic energy. The reconstruction of the hadronic energy, here we are going to call it recoil energy. depends in a couple of constants. This alpha constant, a global constant, and Ci, there is a constant that depends on the region where the event is, the region in where that the energy deposition is calculated. So this is the definition of recoil energy, depending on these two constants, and also in the hadronic energy, in the recoil energy that Gini generates. The constants are there to account for energy that we cannot detect. The alpha global scale factor accounts for final state interactions, neutral particles, binding energy of the struck nucleon, and the energy leakage. Energy leakage, we refer to the energy that goes out of MINERVA we cannot detect. And the calorimeter constant for each subdetector accounts for the energy loss in the lead and steel of the calorimeters. These constants, there was a study that varied these parameters, but did not improve the resolution, so they are fixed. We still have to calculate the alpha global scale factor, and we do it by minimizing a function that constrains the ratio of the recoil energy reconstructed to the recoil energy true generated by Gini. When we minimize this via munit, we extract this value of 1.51. And this function, as you can see, is dependent on arcotangent. We use this function, this dependency in arcotangent, because arcotangent is less susceptible to the high values of this ratio. With this in mind, we look at the beams in true, in the generated hadronic recoil energy, and we look at the fraction resolution of the energy. And we get the fit for this, and this is giving us the resolution of the calorimeter. The first term is a constant term, and basically represents what the imperfections in the calorimeter reconstruction and in the calorimeter construction and temperature gradients, things that don't depend on the energy. And the stochastic term tell us about the fluctuations related to the physical development of the shower. So we can see that the resolution of the calorimeter gets better for high energies, and that at high energies, the constant term is going to dominate. So these are the results for our reconstruction of the hadronic energy. So let me talk about the requirements, the other requirements that we have for the event, for the reconstruction of an event. So let's begin with the cut in the neutrino energy. So because the protons are produced with 120 GeV of energy, we cannot have a neutrino energy with greater than 120 GeV. So this is a safe cut. And then we impose a cut in the muon energy from 2 to 50 that ensures the minimum energy that needed by the muon to get from MINERVA to the MINOS detector. And also the higher boundary give us enough statistics from DIS. The MINOS acceptance is basically a consequence of the geometry limitations that we have for MINOS compared to MINERVA. This refers to the maximum angle that we use. And to the fiducial volume, it's a volume where the reconstruction is more efficient. Okay, so how do we measure the muon? MINOS is a magnetized detector, and it measures the muon by curvature or by calorimetry. So in MINOS, to measure the curvature, we impose a cut in the curvature to be at least of 5 sigma significance. And also there is a cut in the distance that the muon has to be from the coil. Here I am showing you the overlapping area of MINERVA, the MINOS detector. So the coil is used to produce the magnetic field inside MINOS. And through them, we have high current. So to avoid the imperfections that this magnetic field close to the coil produce, we impose a minimum distance of 210 millimeters to 2,500 millimeters. Okay, but those are the requirements that I need, but we are still missing our signal, the cutting our signal. So I'm going to talk to you about now about the shallow inelastic scattering analysis. First of all, let me define some variables. So here I'm showing you a Feynman diagram with the form momentum of the nucleon, the form momentum of the neutrino, form momentum of the muon, and the form momentum of the product, P sub X. Using form momentum conservation and at the laboratory frame, we can extract the invariant mass, that is the invariant mass of the hadronic of the products, and the form momentum transfer. Form momentum transfer is dependent on the variables of the muon and the energy of the neutrino, and also the mass of the muon. The invariant mass is dependent on the Q square and the mass of the nucleon and the hadronic energy. This is a variable that we are going to use. This is called Bjorken X. We are going to use this to extract our cross section. And basically, this is the ratio of the form momentum transfer to the hadronic energy. The inelasticity, Y, give us the fraction of energy given from the neutrino to the hadronic system. Okay, so channel inelastic scattering technically is non-resonant meson production with no quark fragmentation involved. This, in kinematic terms, we could say that is non-resonant meson production with Q square less than 1 GeV square. So this is because we can interpret the form momentum transfer as a capacity of the interaction to probe a quark if Q square is large, or just a nucleon if Q square is small. However, we know that non-resonant and resonant meson production intermix. They live together in a range in W. And they cannot be separated event by event experimentally. The scientific community uses an artificial cut in 2 GeV to separate this intermix from DIS. With this in mind, we can simplify this technical definition in a practical definition as all the charge current events from 1.1, or it's the same to say where the pion production begins, to 2 GeV. DIS is defined as an interaction with higher Q square transfer and W greater than 2. We still can have another definition of SIS based on what we can measure. So on the right is the generation of events in MINERVA. This is an inclusive sample. So there is no kinematic cut on these events. We can identify the first peak as the quasi-elastic contribution. The second peak is identified as the delta contribution. And the rest of the distribution is the interferences of the resonances, non-resonances, and DIS. So the peak of the delta dominates the pion production, and the non-resonant contribution is much smaller. We can, to avoid this contribution, we can move our first low boundary to 1.5, where the smearing of the delta ends. And then with this, we can finally end with the definition of our signal that we are going to use in our analysis. That is all the charge current events with invariant mass between 1.5 and 2 GeV. So we defined already our signal, but let me talk to you about the motivation for this analysis. First of all, of course, is physics. We want to understand how the physics of quarks from DIS meet the physics of hadrons from resonance and non-resonant pion production. The deep underground neutrino experiment, a long baseline oscillation experiment, is expected to have 50% of the events from SIS and DIS regions, and 30% of the events from DIS region. Here, it's an overlapping of the two fluxes. The flux that I use in this analysis, MINERVA ME, and the flux for DUN. So for these reasons, we want to simulate well the SIS region. And we know already that the Monte Carlo neutrino event generators predict different cross sections for SIS and DIS. Here in this plot, you can see the prediction of cross sections for 3 different generators for neutrino energy of 6 GeV in iron, in W, in baryon mass. So there are obvious differences. And yeah, so we want to understand why, and we want to tune these differences. So no other experiment has concentrated on this kinematic region. And this is the first measurement of the neutrino cross-section in the SIS region. So let's talk about how we calculate the background now that we have this defined our signal. So we have to define first templates. The templates are all the regions that are not signal. They are used to estimate the background in the signal. The background estimation is dependent on the models used by the generators. And we want to decrease that dependency. Here on the right, you can see the events coming from these templates, how well we are reconstructing them. I want to be clear that these templates are defined in the truth space in W. So here we are seeing the reconstruction of this variable. So in order to decrease this dependency of the background on the models, we constrain the Monte Carlo to the data. And to do that, we use regions called sidebands. So the sidebands are defined in the reconstruction space in W Reco. And we want to define the sidebands in order that they represent very well the background. To do that, we define them with a gap of distance from the signal. This is the signal region. And so, but we don't know well how the width of the gap should be. So in order to do that, we look at purity of these two sidebands. How much of the events are coming from the templates and are reconstructed in these two sidebands as we move this boundary to low W or to high W. So the same for the gap 2. We move this boundary to high W and low W, and we look at how, with a fraction of the events coming from the template DIS are reconstructed here. And also how the fraction of the events that coming from the signal are reconstructed here. So we define that by looking at the purity and the contamination and also the efficiency reconstruction. And the idea so ideally we could choose just one point where the purity is maximum and the contamination is less. So that is what we have to do. However, for example, for this first boundary, we see that we can sacrifice a little bit of purity to gain at least 22% of efficiency. On the right, we start already with less purity than on the left boundary. So we cannot sacrifice efficiency. We cannot sacrifice purity for efficiency. And even if we do, we won't have the gain that we got here of 22%. So the value set for this is 1.3 at the beginning of this gap and 2.3 at the end of this gap. The gaps are going from 1.3 to 1.5 and from 2 to 2.3. Okay, so once we have defined the sidebands, we want to do the tuning in the sidebands and extract the scale factor that is going to represent the constraint of the Monte Carlo to the data. We use the momentum components of the muon because they are very well reconstructed, and also they discriminate events of different kinematic regions. We look at the events per beam in the data and the Monte Carlo of the distribution of these two variables in the sidebands, and we extract, we minimize the chi-square. Minimizing the chi-square, we extract a scale factor for each sideband, for each variable. So we can see that the difference between these two scale factors is at most of 2%. And I am not using all the data, and we expect that using all the data to have more difference in the scale factors and be able to choose better which one to use. For this analysis, I'm using the longitudinal muon momentum. So with this factor, before using the factor, let me show how is the population of the sidebands from the templates. So we have sideband quasi-elastic that, as we expect, should be more populated by events coming from the template quasi-elastic. The sideband resonance also more populated from the resonance template events. The sideband DIS, the same, more populated by the events from DIS template. When we apply the scale factor correspondent for each of the templates, the agreement between the Monte Carlo and the data is better. Okay, so we have tested and we are seeing that this constraint is working, but this same constraint has to be applied in the signal. So let's look at the signal. These are all reconstructed events in our signal region. I'm showing you here Monte Carlo, the red line. The black points are the data, and the pink area at the bottom is the background. The pink area surrounding the red line is telling us the total error, systematic plus statistics. When we tune, so the background, of course, increases, the area at the bottom, and the total error decreases. So let me explain you now why is the total error decreasing. For that, let me talk to you about the systematic uncertainties. So systematic uncertainties are quantities that we don't know or can measure perfectly. The main sources for these uncertainties are the flux, the interaction models used in Gini, and the FSI models also used in Gini. The FSI refers to the final state interactions, refers to the interactions of the particle inside the nucleus before exiting the nucleus. And the third main source would be the detector resolution. So the systematic errors are calculated by extracting universes. We use universes to calculate the systematic error. So here I'm showing you an example of two universes systematic error. A universe is a distribution coming from a shift in the parameter that we want, in the variable that we want to measure the systematic. So if we want to measure the systematic error in this blue line, that in that distribution, in that magnitude, we vary one parameter in which this magnitude is dependent. Varying one parameter, we create another distribution. For example, here, that distribution is higher than the blue one, so it's shifted up. If we create another universe, could be shifted down. So the systematic error will be the average of, for example, in this beam, the systematic error would be the average of this difference plus this difference. So using this method, we create a systematic error for all the systematics that I'm going to show you. However, depending for the flux, we use 100 universes. And for the detector resolution, we use 60 universes. Most of the universes, most of the errors for Gini have 2 universes. Okay, so this is a breakdown of the ping area that I showed you before, the total error. And colors, the line colors are showing the different systematics, and the dash line, the statistical error. The black line is showing that the total uncertainty, the systematics plus the statistical. When we tune, what we see before, each of these systematic errors decrease. So this is because, as I said before, each of these systematic errors is coming from a number of universes. So this is produced because each of those universes are suffering the same procedure of constraint that I showed you before, and that cause a pile-upping of the tuned universes to the Monte Carlo. Okay, so but the goal is the differential cross-section, and what I have shown you until now is the selected data and the constraint background. We have to talk about the unfolding and the normalization constant, the efficiency, the flux, and the target, and the beamwidth. So the beamwidth is chosen creating a migration matrix. So to create a migration matrix, we state a couple of requirements: a minimum efficiency of 58% and a fractional error of 10%. On the top, and the plot of at the top, you can see the migration matrix. The y-axis is the true BRKNX, the generated values, and the x-axis represents the reconstructed beams. So each of these numbers is telling us the percentage of generated events in each beam, reconstructed in each beam. This is what we call the efficiency. So our requirements are constructing this migration matrix. The idea is to create a migration matrix with efficiency greater than 50%, and then look at the beams and decide what beams to fusion depending on what physics we want to see in each region of the variable. For the first study, we began with these 2 requirements. At the bottom, you can see the matrix showing the relative sizes of the beams. Okay, so unfolding is the procedure for correcting the distortions and smearing caused by our resolution in the detector. We want to extract a true distribution based on what we measure, that we are representing here as y, and the true distribution as lambda. So we want to extract this matrix that apply to the measurement. We extract the true distribution. This matrix is called the smearing matrix. However, this simple calculation brings problems if the matrix is singular, and also it cannot handle large statistical fluctuation caused by the minus sign in the inversion of the matrix. For that, we use the D'Agostino unfolding. So the D'Agostino unfolding basically is an iterative process in which we choose an assumed true distribution, and we iteratively make it closer to the true one. We use the Bayes theorem for that. And the Bayes theorem is this one. So we have the smearing matrix. We use the migration matrix of our Monte Carlo and the initial probability distribution that we are assuming. So we assume this initial probability distribution based on the best knowledge that we have of the process. For this assumed distribution, we extract an smearing matrix. With this SMERI matrix, we calculate the unfolded events corresponding to this SMERI matrix. We then we compare these unfolded events to the initial events. The initial events are the events related to the initial distribution. If this is not close to 1, to the chi-square over the number of degrees of freedom, we replace the initial distribution by the distribution that we got, and we repeat this process. So this is an iterative process, and this study was done with 8% of the data, and 5 iterations were used. So this is the result of the data minus the background for Bjork and X. When we go through the unfolding, we can see a slightly shift of the events to higher Bjork and X values. The uncertainties are in progress. I am working still on that. Okay, so let's talk about the efficiency. So the selection cuts that remove the backgrounds are also going to remove some fraction of the signal. So basically what we are saying is that our reconstruction is not perfect. There is also intensity efficiency dependence. The increment of intensity in the NUMI beam caused that the reconstructed per POT events decreased. So the efficiency is basically all the reconstructed SIS events by all the events generated. Here I'm showing you the efficiency for Bjork and X, and it decreases for higher Bjork and X. So the other two, target and flux. The flux is simulated via GM4. Also, we use to correct the flux all available external hadron production data. And specifically in MINERVA, we calculate a constraint from a neutrino electron elastic interaction. On the plot, you can see both of the beams that MINERVA was exposed to. And in this study, the medium energy is used, the medium energy beam. So the targets, we have to normalize by the number of nucleons in the tracker region so that our cross-section will be independent of the size of our detector. Okay, with all these elements, we can calculate finally the differential cross-section. This is a preliminary result. And for this preliminary result, we can see that the SIS data is shifted to higher Bjork and X. Or in other words, we could say that there's an overestimation of the Monte Carlo at high Bjork and X and an underestimation of the Monte Carlo in higher X compared to the data. This is the first measurement of SIS region in the world. And we also want to compare this SIS region to the DIS. And this is a result that hasn't been published yet. So looking at both, we can see that the SIS peaks at a lower Bjork and X than the DIS cross-section. This makes sense because for DIS, we are requiring a greater Q squared. We are not requiring we don't have a cutting Q squared. Okay, so yeah, so those are the main two conclusions of my analysis. So let me talk to you about the present and future of this analysis. The analog analysis in antineutrino is right now in progress. Machine learning vertexing had been implemented in MINERVA only for deep inelastic scattering studies. Currently, this implementation in the tracker region for SIS studies is in progress. Other members currently involved in the SIS analysis are Gilson Correa, a postdoctoral researcher, and Adrian Lozano, a PhD candidate, both from CBPF. A master's student is expected in early 2021. And yes, so this analysis is expected to be published next year. Thank you.
Okay, thanks, Jean, for your presentation. So now we start the questioning from the committee, and we start with Dr. Jorge Morfin from Fermilab. Dr. Morfin, please.
All right, thank you. Thank you, John. That was a very significant and important first step in an analysis that's going to continue for some time. Could you outline what you think the next steps should be in the analysis of the SIS region? In other words, you have just used a small percentage of the data and you...
Professor Jorge, o senhor pode abrir seu vídeo, se quiser.
Jorge Morfin, you can open your video if you want, so we can see you.
Thank you very much. I would like to do that, but unfortunately the video camera on my computer has been down since April, and the Fermilab computing department has said it's a hardware problem and not easy to fix.
Yes. Okay, so yeah, the first step, the immediate step, is first to use all the data and reproduce this result. Produce a result with the same meaning to make a good comparison, a correct comparison. And then we are thinking about looking at different regions of W, because we know that the contribution from resonance is higher until 1.7. And then, so there is resonance and non-resonance from 1.5 to 1.7, but the contribution from resonance is higher. At 1.7, the contribution from non-resonance increases until 2. So we are thinking about doing the analysis in two parts of W, one from 1.5 to 1.7, and then to 1.7 to 2. And once we done that, I think the next step will be to start thinking about applying a Q-score cut to separate the to make a comparison to DIS also.
What about other variables? What other variables would you suggest we need to study?
Oh, okay. So for this study, we're using BjorkNX, but for this same region, we can use another variable dependent on Q-square. Let me show you. I have it here. Okay. Okay, so Q-square is a variable that has an important interpretation as the fraction in the nucleus total momentum carried by a struck quark when Q-square is very high, when it tends to infinite. In our study, of course, we have a Q-square finite. And this Q-square finite start with this Q-square finite, we are sensible to the effects of the mass of the target and the quarks. So we can use another variable that is dependent on Q-square. And this variable is called the Nachman variable. This variable, as Q-square tends to infinite, it tends to be BjorkNX.
All right, you've introduced now the Nachman variable, which is used for making what's called target mass corrections as you come out of the deep inelastic scattering region. This tends to introduce the idea of duality. Would you like to comment on how your essentially inclusive cross-sections in the SIS region can contribute to duality studies?
Okay, so the idea of duality is to make an average of the DIS structure function. So the average of the structure function of resonance is going to be the extension of the structure functions from DIS. So I think for that study, we'll have also to use the variable that is dependent on Q-square. But yes, I think that's one of the next steps. Try to find methods to test this duality. If we can, we are going to think about that. Yes.
Yeah, I think that could introduce a very long, interesting discussion, but I don't think it's right for this time. I think what you've done is introduced the total inelastic cross-section between 1.5 and 2 GeV squared, or 2 GeV. And that is essential for the eventual application of duality studies in neutrinos. So let me just go back and ask you some more details on the sideband tuning.
Sure.
I noticed that what you've used in your sideband tuning has been the longitudinal muon distribution. But of course, there are other important variables that you could use, such as the transverse muon variable. How does the tuning look in that? Do you have by chance that as in your backups?
No, but just so here you have the tuning for the transverse muon momentum. And yeah, the difference between these scale factors is at most of 2% especially for the resonance. And yeah, so because we are working with a part of the data here, the difference between the scale factors is not too obvious. So I choose to extract the result. I choose the longitudinal muon momentum, but I hope to, when I use all the data, to have a better discrepancy and make and be able to have more information to be able to choose one.
Right. I was more looking for actual figures that show what the tuning looks like, whether indeed just a single variable to scale from the sideband to the signal region is sufficient, or do we have to worry about the shape as well?
I understand. Yes, so I did that study, but I don't have the plots now.
Okay. So the final question I'd like to bring up is about your results. If you can go back to the X distribution, your final value. All right. So as you point out, the X distribution for this shadow and elastic scattering does indeed peak at lower Q squared, lower X, and it's because of the fact that there's this Q squared cut in the DIS. But it also is peaked, it's shifted towards high X. What does that imply as far as if you were thinking of a parton distribution function interpretation of your result? What's going on?
As the parton distribution function. Okay, so what I can say for this shift to higher data is that so what we saw in the sidebands is that this discrepancy, the same discrepancy that we are looking at now of the overestimation of Monte Carlo to low Bjork and X, is the same discrepancy that we have in the sideband, in the resonant sideband, at least for Q squared, that is proportional to Bjork and X. So that makes me think that this shift is coming from a contribution of the resonance event, the sideband at lower W. So this contribution of the resonance events are causing the data shift to higher values. So it's telling us that the resonances tends to have a higher Bjork and X for an interaction. in terms of the Parton distribution function, so I know that Bjorken X is, we can express, so Bjorken X has an interpretation in the DIS region at very high Q-square as the fraction of momentum of the nucleon containing the struck quark. Right? But
right.
So I think but this interpretation is made to high Q-square. And if we want to get this same interpretation, we would have to correct for these values of Q-square finite. And I think we had to look at the Nachman variable distribution to get a better answer for that question. Because Nachman distribution is a scaling variable, but it corrects for our events with Q-square finite. Yeah, I think that would be my answer.
Okay, that's a really good answer. It's leading us to the idea that I wanted to bring up, was that what your results are suggesting is that the current version of Genie that you used in the simulation program, is underestimating the importance of the up and down valence quarks, which can then also be interpreted as you have. It is underestimating the resonant and or non-resonant contributions that are necessary in the data to explain, that are necessary in the simulation to explain the data, so that the simulation has underestimated the number of non-resonant and resonant events that we see in the data. I think that's a good first step. There's a lot left to do in the study of the SIS region, but a nice result that you've got here. Thank you. That's all I have.
Thank you. Thank you.
Are you done? How are you?
Yes, I am done.
Okay, thank you very much. Now we go for Dr. Ana Amélia Machado from Unicamp. Ana, you may open your camera if you want, please.
Hi. So thank you for this invitation, for making part of this committee. And thank you also for Jan, because after his presentation, everything that seems to me unclear when I read his PhD was totally or almost totally understanding now. I have some questions and also some suggestions that I would like to do now. So, Gian, do you have also your thesis open in your computer also? Don't need open, only to ask you.
Okay, let me. Yes, give me 1 second, please.
Okay. Or I made a lot of suggestions in the right version, and I can only tell you, don't need to see now. But okay. My general comments about the thesis is that you need to describe it better, all chapters, because the same way that you did now in this presentation. For example, in the introduction chapter, you can make talking a little more about what you will describe in each one of the chapters. So you can spend, I don't know, one paragraph to say something more, not only write the same thing that you did in the index.
Okay.
So from point of view of the history of neutrinos, I think that is complete. You was really good to write this part there. And also for the standard model. One suggestion is that in this section, you introduce the first time the abbreviation of neutral current interaction and charge current interaction. You can use also, since this chapter, the abbreviation. Probably is better. Sometimes you use NC, sometimes you write neutral current. So
yeah.
This is only a question of makeup of your text.
Okay.
And when you show the matrix, the mixing matrix of the neutrinos, I suggest you, because this is an experimental thesis, that you made some connection with, or only tell us in this point, which was the experiment that was built to do each measurements about the angles and the phases. So here you could talk about that experiments. I know that you did this in the following chapter, but you can only do some reference there.
Okay.
And the last equation that is the probability of the oscillation, the 2.10. You can also tell a little more about the parameters that we have that we can have under control, because when we do a oscillation experiment, we must know which parameters we can control it and which one we can measure. So this is a good information that I think that you can tell you in this point. For example, I know in the long baseline or short baseline, I know exactly where I will put my detector because of this equation, and also the energy of the beam that I will produce. Now in the following sections, when you show current and neutral charge and neutral current, my suggestion is that if you are able to add the Feynman diagrams, will be much more easy for someone to see these interactions.
In what,
as you did
in what section? Excuse me.
2.33 subsection and 2.3. So you did this in the follow subsection.
Yeah, I put them all together, but yeah, maybe it's better just to put it in each section. Okay. Yeah. Okay.
There is this kind of corrections on this. When you talk about the neutrino oscillation experiments, I think that you can write a little more the introduction and the importance that this kind of experiment, the link with your work in this thesis. Here is the moment to write that, because you describe some experiments, but you cannot understand why you are doing that. Okay.
Okay.
And at the end of this section, you talk about the neutrinos from accelerators. And here, I think that is the moment that you do the connection with Dune. The importance of your results in MINERVA that can be used in Dune experiment. I think that is a good moment to talk about Dune, as you did in your slides, in one of your slides. That is page 8, slide number 8, I think so.
Yes. Okay.
Can you go there, please?
Sure. Yes, here, 23.
Yes, this one. So I really like it when you present this plot here. Probably you can copy and paste in your
Yes.
work. Okay. Okay, chapter 3. So after your presentation and discussions, I could understand better. This is the first time that I study in deep this subject, because it's not from my area. But I had some doubts about the plots that was made by you or by the collaboration. But now I understand that all of this is from your work. And we reached the MINERVA experiment. Here, it's really important, Gian, that before to enter in the section 4.1, you describe MINERVA. Because first thing we need to understand how is the goal. And you did this in your slide number 11.
Okay. This one?
Yes, probably you talk about. But it is important to understand how is the goal of this experiment. Us is writing in the web page of the experiment. When I reach this moment in your thesis, I go there to understand better the goals of MINERVA, the proposal, and a lot of information. For example, I would like to know how long time in MINERVA take data, and
Okay.
if there was some time that was a dead time, I don't know. I see that sorry?
I have a plot showing for the medium energy. So I know that MINERVA has been taking data since 2010, but I think I have here. Yeah, so.
Perfect.
Yes, yeah, this is, so so the intensity of the beam is measured by the quantity of protons that collide the target. And this is showing the data taken from 2013 until 2019 for neutrino and antineutrino. And yes, so these are the two beams, but this is showing just the evolution in time for the medium energy beam. The total POT is for neutrino and antineutrino. I don't have the evolution in time for the low energy for this other flux that is picked at 3 GeV. But yeah, so these are the total flux delivered.
But the higher energy that have been observed in MINERVA was more than 6 GeV. I don't understand if you use the data only with 6 GeV, and this was the highest energy that MINERVA reached, or there is?
Oh, this is just the flux. So the flux is picked at 6, but the tail goes at more than 50.
Okay. So here I think that you needed to describe a little more about the MINERVA. It don't need to be long, but it's important before to start to talk about the beamline.
Okay.
Yes, I see that you put this graphic after that. But in any case, you can say some words there.
Specifically, could you tell me in what part, on what page?
From your thesis is page 22.
Okay.
Is an introduction before to start, so I don't see the description of the experiment in few words. If I enter in the web page, and if you look there, you can understand what I would like that you write there.
Okay.
But of course, I comment this here. Some pictures in your thesis, it has a low resolution, so I suggested that you change if it's possible.
Yes, yes. Yeah, I found that's what I saw, especially one for the Minos. Yes, I'm gonna change that.
And I am curious about the scintillating strips. I would like to understand one thing. If you have, for each prisma that you have, so you are seeing events that interact inside that prisma, right? My question is, each one of that prisma is reflective by your, is a modular detector or is a unique volume detector?
Let me go to that.
If you,
yes,
if you go in your slides, this page 2.
This slide, I put the slide of this.
Yes, here.
Integrator strip.
So if you have an interaction in one of these prisma, you can see by the optical fiber that is in the center of that. But you can see also some signal in the adjacent prisma or not.
So ideally, they are containing the light via total internal reflection. But yes, there should be some light going to another one. Yeah.
And this?
If I may interrupt.
This is in the borderline, you know?
Yeah.
Yeah.
If the event happen in the borderline of the prisma.
Jorge Morfin, want to say something?
Yeah, I just wanted to add more about the details of what we were trying to do with this triangular shape. And that is indeed the light is contained within one of the scintillator strips. And then as the particle proceeds through the next scintillator strip, we are able to use the concept of charge sharing to better localize where the particle has passed through subsequent strips. So just one alone is not enough. We need it to tell us what the charge is in the adjacent strips as well. So it's charge sharing that's important.
I think that Anna wants to know if there is some crosstalk.
Oh, yes.
Light crosstalk.
Yes, there will be crosstalk, but we have studied it carefully and tried to minimize that effect in the eventual statement for the resolution.
Okay. I would like to understand how can be totally or almost totally reflective each one of these. This was my debate, but okay, I understand.
Anna, just an observation. The photo doesn't show clearly, but the prisms are all covered. They are covered with the oxide that makes them reflective.
See. Yes, the titanium oxide, no?
Yes.
I think that is this one.
That's the titanium dioxide, right?
And also in the detector section, when you finished to describe all elements of the detector, you made a subsection about the minus. I think that you needed to link why you are talking about minus. Okay. You are describing all the detector's components from MINERVA, and then you talk about minus. So this should be more explained here. I think that in this moment I can ask you if you did some work in hardware way.
In what?
Did you have a possibility to work in hardware?
No, I had the chance to work in the calibrations, but the framework, the computational framework for the calibrations were already set. So I had to learn and identify how to identify the problems, but I didn't have the chance to go underground. I went just 3 times, but I didn't have the chance to work on hardware.
Because when you start to work, the experiment was running.
Oh yeah, so actually, yeah, it stopped. It stopped taking data last year on February 2019. Mm-hmm. Yes.
Another thing that I found, I didn't find in your thesis. So Jenny is a software that is from MINERVA collaborator, or I didn't find the reference.
So Genie is a neutrino event generator, and it's also a collaboration.
Okay.
Yeah.
So, and the Monte Carlo you used was using this program, also
yes.
Giant4.
Yes, of course. The generation of the neutrino events are made using Genie, and then the propagation of the particles produced through the detector is using Giant4.
Mm-hmm. And what was the software used to make your analysis?
So here we use root.
Okay, it's good if you do the reference for that.
Okay.
Can you go to the page 27?
Sure.
Sorry, the last question about the experiment before this one is all data that you used came from Intuple, or is a raw data?
So yes, for a specific study, the tools are producing one Intuple with all the information, and then we select from that Intuple. Okay. Yes, we use Intuples.
Okay. And the cuts you mentioned in your thesis is default cuts made by the collaboration, or you made some cut studies there?
So, yeah, most of the cuts that I mentioned were already set for from inclusive analysis before, and also for DIS. And yeah, we make some variations, like in the angle acceptance, because it's in the tracker. Yeah.
It's important if you point the cuts that you manage to improve your results.
Okay.
So now the page 27.
27. Yes.
I am seeing the page number 12.
Page 12?
No, I am seeing the page number 12, but I would like that you go to the page 27.
Okay, I am there.
Are you talking about the pages on the thesis or the presentation?
No, the presentation, sorry.
Oh, okay, I thought you were, okay, slide
Sorry,
27.
Jan.
It's okay. Yes.
So this was, I think that I made a lot of confusion during when I read your thesis, because I could not to understand what means signal. So this is a background signal, right?
Yeah, so this is, I had to make it more clear, but the templates are defined in the truth space. So this is what Genie generates. And the templates are everything that is not signal. And the sidebands, I made that mistake. I should have called it a signal region. And yeah, that's in the sidebands, this is defined in request space.
Okay, this is your signal that I'm seeing in the sidebands.
Yeah, this is what we are going to, this is a reconstruction that we are going to look at and consider as our result, yes.
And you mentioned that you don't use all events that are available for you. How is the percentage of events that you use?
How is the, excuse me?
How is the percentage of the events that you used in this analysis?
It's 8% of the whole data that I use. Yeah, so the idea is first to set the machinery running and extract cross sections with all the steps done, the systematics and all the details, and then start producing all the data, all the Monte Carlo. Start using all the data and producing all the Monte Carlo. So yes, this is the next step that I'm going to be doing.
Then practically in this moment, you have all codes ready to analyze all the events. And you are doing this in the next, I don't know, 1 month. So your paper, we will include all of events you have, right?
Oh, yes. Yes, for any publication in MINERVA, all the data has to be used.
And how much time is needed for review of the collaboration? This is only a curiosity.
That varies depending on the analysis and on the problems that could be found, but maybe yeah, it depends. 4 months, 5 months, maybe half a year.
Okay.
Yeah.
So only to be sure that your paper will be done for next year.
Yes.
So the slide number 31.
I just to call attention that sometimes the collaboration itself is much more demanding than the referees. So it sometimes takes longer.
Yes, I know. So here, for the first, no, it's only a comment because we cannot see the signal for the first one. I don't know if you change the scale or use a logarithm ones. I don't know what is better, but it's only a comment.
Yeah, so yes. So it's expected not to have signal because this sideband is far away from the signal. So this is what we want to show, we want to look at.
And I had some doubts about the systematic errors, but you will answer me in the slides 36 and 37. Now I understand how can you go there?
Yes.
Yes, this one. Could be, I think that you could be more clear in your thesis, but after seeing your presentation, I think that the doubts was a really hard work to do that, no?
The systematic is already set. So this systematic is already set in MINERVA. But yeah, these are set for DIS and for inclusives. But when we change the region that we are looking at, there are details that come up and we have to fix for them.
Okay.
So that's also why the propagation of the folding is it's not finished. Yeah.
And my last question was about the perspective that I was missing in your thesis, but in your last slide you show and explain very well. So I think that it's good if you add this information in your thesis. So this is what I wanted to suggest and ask you.
Okay.
Are you done?
I'm done. Yes, I'm
okay,
done.
Thank you very much, Anna.
Thank
okay,
you.
now we go to Dr. Giovan Alves from CBPF. Giovan, please, you may open your camera if you want.
Okay, thank you. Can you hear me okay?
Yes, I can hear you.
All right, so I thank you for the invitation, Elio, and also Gian for explaining a lot of things to me. We already have a conversation, so it helped a lot to understand some of the things. So thank you also for that. Okay, so one of the things, can you go back one slide, please? It's yeah. So the data that you have there, I'm quite surprised that you have those. Where's the statistical error? You said that you don't have all the data there, but you have the error bars are so small I can't even see that. So I don't believe in this in this plot.
Yeah. So the statistical error is so here you can see the statistical error before going through the unfolding. The problem is that the unfolding is messing up with my uncertainties. So the problem is here.
Okay. Yeah.
Sorry about that. Yeah. So after this, that's we are just looking at central values.
Yeah, because I found it strange that the statistical error just vanishes somehow.
Yes.
So,
yes.
So that was interesting. Okay, so a very general comment. You showed in slide 13 and 14 some event display, and I really like that. And why they're not in the thesis, man? This is a great you know, a very nice example of some events that you see in the detector, and you should have shown that in the thesis, because this is very nice. You can see very well how the detector works, you know, how it you know, how the resolution more or less works. So this is a great thing to have in the thesis, and I really think you should put in the thesis some of these event displays there. But, you know, just to show the people you know, how the detector works and how do you see the events in the detector. It's really great. So okay. Okay, so in the slide 15, I don't quite understand this alpha thing.
Yeah.
You said that the alpha is a global thing, right? It's a global.
Yeah, it's a constant. Just
it's a constant, but you have put there energy leakage. Energy leakage. So this should be energy dependent then, right?
Yeah. So I understand that this energy leakage refers to the so if an event is close to the borders of MINERVA, and then there are energy that is coming outside of MINERVA, and then would it be detected? So the one that is energy dependence is the C sub I, because this depends on what energy has the particle going through the lead and steel. And there was a study made already in MINERVA, and they saw that this using this factor in a minimization and getting different results didn't change the resolution. So yeah, they were fixed. And the only one that we have to track for this is the global scale.
Yeah, I'm still confused because
yeah,
you know, energy leakage should depend on the energy, because if you have a high energy particle, the leakage should be higher than a low energy particle. So I'm a bit confused. Yeah, I still don't understand that.
Okay. Yes, I understand. Okay. Let me think about that. I could answer you later.
Yeah. Okay. Yeah, but I mean, we have you know, all the I work in 2 experiments, and of course the colorimeter has this punch through thing, and that's dependent on the energy, because you know, higher energy particle have higher punch through. You know, the hadron can punch through the colorimeter and go to the muon detectors and things like that. So that's what my impression is, that the energy leakage should be energy dependent. But then, well, later you can catch me later with that.
So this punch through is the same as, so it's particles that are exiting the detector where you want to measure the hadronic energy, and they are going to another part of the detector.
Yes, that's right.
Okay.
You have a hadronic colorimeter, and you have a very high energetic hadron that punch through and go to the muon detector. So that's a leakage of the. So you lose some energy there. So I mean, that's what we call energy leakage. But anyway.
Okay. Thank you.
Okay, so on page 22, I mean slide 22, actually, you have this distribution. I understand this is Monte Carlo, right? This is not beta.
Yes, no, it's Monte Carlo, it's Gini.
Okay, yeah, because I saw in the thesis, and somehow when you explained this picture, it gave me the impression this is data, but this is not data. Definitely, it doesn't look like data. That's the many too smooth to be data. Anyway, just to clarify, this 27, slide 27, you have this template. I already talked to you about this. I think Anna also. I think this name template is a very bad name. You should try to change this thing, because template means anything. You can have a template of data. You can have a template for Monte Carlo. You can have a template for signal, for background, for whatever. So templates can mean anything. At least in the analysis that I've seen, they have templates for signal. They have templates for Monte Carlo. I mean, for background. They have templates for sidebands, whatever. So maybe you should use a different name, so not to confuse people with that. Okay. I mean, that's my impression.
I think yes. I think the name template comes because these regions are fixed relative to the sideband that changes, because the sideband changes depending on the gap that we choose. So maybe, yeah, I think they put this name because the templates are regions that are fixed, and the sidebands are going to change depending on our signal contamination, on how much we want to see, how much we can avoid, how much region of intermix with signal contamination and sideband, that is the gap we can avoid. Yeah, maybe, but yes, yeah, it's also a first word for me. Okay.
Yeah, one thing about the systematics, I think it's like, I think it's 35, if I remember correctly. I think it's, let's see, 35. Yeah. So you when you calculate the systematic, you use this multiverse thing, the multiple universes. So how do you actually find out how many universes you need? I mean, you can use up to 100, as you said in the thesis, but I mean, what's the What's the criteria to use 100 or 50 or whatever?
Yeah, so the main criteria is the number of parameters in which the flux depends. So the flux depends in more parameters than the detector resolution. And that it needs more universes to calculate a systematic. So yeah, that's the main differences on why the main criteria on why the different number of universes were used. And there were studies done to choose this number, studies testing for high universes or low universes.
Mm-hmm.
Yeah.
Okay. Yeah, one thing I completely forgot. It's on my list here. It's in slide 17, 17. I talked to you about this already.
17.
17, yeah, 17. I really like to see a picture of Minos. Come on, can you give me a picture of that detector? I can't understand why it's so difficult. I've seen some teasers. I've seen, I think 3 teasers already from MINERVA, and they don't put a picture or a good description of the Minos detector, which you use for your analysis, by the way. So, I mean, just a good picture showing for example, the coil. I don't understand how this thing works. How the coil, how's this thing winded around the iron or something? I don't know. I mean, you have the steel plates, you have some coil going somewhere that I don't know. And I mean, seeing this picture,
Okay.
I do not understand anything. I mean, I'd really like to see a nice picture of the Minos detector so I can understand how the magnetic field is oriented. Is on the horizontal, is on the vertical, whatever. I don't see it here. So some things like that, you know.
Okay.
To
Yes.
clarify a little bit, you know.
Okay. I'm gonna put a better figure describing the Minos detector. Okay.
Yeah, that should just one picture. It's enough. Don't need much. Just let me check here. Oh yes, this one thing that we discussed yesterday, and I totally forgot, is this. Where is that? When you do the when you do the corrections,
Yeah.
do you have the picture of appendix C? That the one I talked yesterday.
Dixie. Let me go there. Excuse me.
Is the one that shows the Bjork and X?
Yes, appendix C. Yeah. So
I can share the screen if you like.
let me share it. I'm gonna share.
You can share.
Yeah.
Yeah. But somehow.
Oh, let me. I can share it if you want.
Okay. Yeah.
Yeah. So.
Yes. Okay. So you can see that most of the verbs are okay when you apply the correction, but I really don't like the Bjork and X. Go ahead. So mean energy, blah blah blah. Okay, that's it. There you are. So this is horrible. The Bjork and X is not very well represented by, you know, when you do the correction. It's you know, you see the data beyond 0.6 is completely off. So you guys should work on this, because I don't think a simple scale factor is going to work here, because Bjork and S is also not you know, a straightforward variable, so it's a combination p square, and so I don't know if you can do just a simple scale factor. I don't think it will work. You know, you got a discrepancy there. So
Yeah.
you have to try to work on that.
Could I
Yeah.
interject?
Please. Yes.
I agree 100% with what you've just said. That's why I also wanted to emphasize that this idea that's used in many experiments to just use a single variable and a single factor, call it a tuning factor, that essentially just adjusts the intensity, but doesn't refer to the difference in shape, is unfortunate. It's a mistake. So I agree with you. You need something more definite to describe discrepancies than a simple scale factor.
Yeah. Yeah, and also because you're going to report the results as a function of Bjork and X, then the whole thing, you know, it loses. It's kind of weird because you have a variable that's not very well represented, and you're reporting on this variable your results. So, well, anyway, you guys have to have a bit of work to do on that. So I guess that's basically all my comments. The other comments that I told you yesterday are about the references. You know, there are several references. There are internal MINERVA documents that you cannot access, and so you have to try to, because I was looking for some references, and I couldn't access because they are on the MINERVA.db, and they are inaccessible from outside. Try to put something like a thesis or whatever. So that's basically all my comments. Thank you very much, and good luck with your analysis. And I hope we see this data coming out soon.
Thank you.
Okay, are you done?
Yeah, sure.
Okay, thank you very much, Ivan. Okay, now we go to Dr. Carsten Hensel from CBPF. Carsten?
Yes, can you hear me?
Yes, we can hear you. You can open your video.
Okay. First of all, thank you very much for the invitation to participate in this bunker. I'm aware that we have a neutrino group at CBPF, but I do not have often the chance to basically catch up on what they're actually working on. And it's nice to see that neutrino physics is more than just measuring neutrino oscillations. That was a very interesting thesis to read, and yeah, thank you very much for the opportunity. I have some very general remarks. There are some typos and there are some errors in the text, which I will send you the PDF document here, and I will not go through them here. But in general, I think that the thesis itself it's well written. It's written in English, something that increases the opportunity to reach a wider audience. It's always good. I was very surprised. It's a very brief thesis compared to other theses, which is not necessarily a bad thing. I actually prefer it this way. On the other side, there are some things that might have done with a, let's say, more explanation or more elaboration. And as Anna already mentioned, there are some things which I only understood, I guess, today in your presentation. Funny enough, there's some plots or pictures you used in your presentation, but didn't use in your thesis, that do a much better job to explain things. And maybe you should change some of the plots. But I made some remarks in the thesis as well. So these are the general comments. I have, however, a few general questions. So the Gini Monte Carlo generator, Can you elaborate a little bit more what's happening there? I assume this is some sort of effective generator that what is behind this this generator?
Okay, I think I have a slide that can give us a couple of. Just 1 second, please. Yeah, so maybe the answer would be so I could answer that based on the difference of this generator to other generators. So I have a slide here. 1 second, please. Okay, found it. Let me share. Okay, so there are 3 generators that I showed, and those 3 are having different origin and also based on the purpose. So Genie is developed by international collaboration, and it's a universal neutrino event generator, and it's written in C++ and it's well maintained. And the other ones depends on, for example, Newt was developed initially for Kamiokande and mainly written in Fortran, and then Neuro is more theory oriented. So Genie uses for the SIS region, basically we are using so basically Genie uses a couple of models, Rain-Sagal that simulates the resonances and low baryon resonances, and Bodek-Yang that simulates the DIS and also contributes to the resonances. So these are basically the 2 models that are using Genie.
I see. So since you see the discrepancy in your measurements, if this persists in the final publication, so could you use your differential cross section then to tune Genie?
Yes.
Okay.
Yes, the idea is to tune Genie, and
okay.
Yep, to create a tune and in this region.
So you would just plug in the measured cross section. That's what's happening.
Yes.
Okay. Good. So the cut between, or not the cut, but the cut between the SIS and DIS region of 2 GeV it's rather arbitrary, right? Or is there some deeper meaning behind this? Because in one of your plots, you showed that this 2 GeV plot is just in some sort of plateau of the distribution.
So you're talking about this slide, or maybe
the hadronic activity. Yeah. So if you look at the page 22.
Page 22. Yes.
Yeah. So if you look at this, you're basically with this 2 GeV just in the shoulder of the distribution. Is this a coincidence, or is this? I mean.
I cannot hear you well.
Oh, sorry. I was wondering about this hadronic activity cut of 2 GeV. So SIS is below 2 GeV. I understand that this is a rather arbitrary choice, but it looks like that in the distribution, it's some sort of peculiar choice. I was wondering if it's just a coincidence or if there's a deeper meaning behind it.
So this is an artificial cut, and it's not a rigid cut.
Okay.
And basically, this cut is to separate this intermix between from DIS, and this cut is ensuring that we don't have DIS, but it's not a rigid cut, so it doesn't mean that we are not having DIS for low, but
no. I
yeah.
understand. Yeah. It's just it's a definition. I understand that.
Yeah, so that's the same for Q square.
Yeah.
Yeah.
Okay. So one of the plots that was much nicer to see in your presentation was about the beamline. So in your thesis, it's very, the transversal dimensions. It's basically it's a guess. You have to guess what the transversal dimensions are. It's much nicer, the sketch you used there in your presentation. And Gillivan already mentioned it earlier. So you use MINOS to measure the momentum.
Yes.
How does it? For me as an experimentalist, these are two different experiments, two different collaborations. How does it actually work then? I mean, you have to have two detectors that talk to each other. You have to have two different DAQ systems that talk to each other. How is that set up?
So the muon in MINOS is tracked. So we see that the track is identifying MINOS, and also the track is identifying MINERVA. And there is an extrapolation of this track from MINOS to MINERVA, and then and there is a comparison of that of that distance that this extrapolation is to the track in MINERVA. And then there's also an extrapolation of the track in MINERVA and another comparison of the distance there. And based on these distances of these two extrapolations in the two detectors, we decide if this is a muon that actually is coming from an interaction in MINERVA.
I see.
And we call that MINOS muon matching. So the muon detected MINOS is matched to the muon in MINERVA.
Can I assume that the MINERVA and MINOS collaborations have a very big overlap on physicists?
Excuse me?
Or are these the two collaborations, MINOS and MINERVA, these are two distinct collaborations, or is there a big overlap on physicists?
Oh, no.
Because
so MINOS has already finished taking data, and we use the detector just for muon just to measure the muon momentum. But yeah, MINOS have finished already.
Okay.
But if I could
Just go ahead, Jorge.
Yeah, I was just going to say that indeed there is an overlap between the physicists on MINERVA and MINOS. And right from the beginning, it was a very important part of the MINERVA collaboration to make sure we understood the MINOS DAQ, and that we had experts on MINERVA that could help the bridge between the MINERVA DAQ and system, the MINERVA framework, and the MINOS DAQ and framework. So yes, that was a very important startup criteria for the experiment.
But in any case, they are two different and separate collaborations.
Correct.
Which is I mean, makes it even more impressive. Then I mean, this is very nice collaboration of two groups. Very good. For somebody who never worked on a neutrino experiment, can you describe the actual neutrino, the structure of the neutrino beam? In your thesis, you talked a little bit about the time slices, etc. So I assume that the neutrino beam, the structure is somehow correlated to the initial proton beam. But how does the data taking look like? I mean, this is a
well, so for my specific analysis, I can show how the data look like. I don't have how the data look like for all the data produced. I just show the evolution in time on how the data was taken. I showed that plot for Anna. I don't know.
I thought. Yeah.
And yes, yeah, I just can show you now how, or I just show you now how the data looks for my analysis.
Okay.
Yeah. Yeah, so basically this is how the data is shown, but I don't, yeah, I cannot show you now how the data shows for all the data, how is the distribution of it.
Okay.
John, do you have the XY distribution of interaction vertices to show what the spatial distribution of the beam looks like when it hits MINERVA?
No, I don't have that distribution. So basically you're asking for the data taking in the different transverse area of the detector?
Well, I may have been mistaken, but I thought the question was, what does the beam look like when it actually gets to MINERVA? And
maybe he wants to know the profile of the beam.
Yeah. It's
the
actually
profile and basically the distribution in time. So basically you trigger your detector every time the proton beam hits the target, or how does it?
Okay. Yes. No, I don't have the plot. Yeah.
Okay. Yeah. So this was something similar was asked already earlier. Slide 35 in your presentation concerning the systematic uncertainties. So we describe the averaging in several universes. So this is done on a per bin basis, and you average the positive deviations, and you average the negative deviations. So in the end, you get a asymmetric uncertainty.
Yes, we average the deviation caused by each universe. So the deviation is the distance from the universe to the central value, and these distances from each universes are averaged, and this is the systematic error. And this is just a simple example for 2, but this is made for 60 universes or 100 universes.
Okay.
And it's per beam. Yes, you're right. It's for each beam we do that.
This was asked. This was already. Yeah, I guess all the other questions were already asked and answered. Well, that's it from my side. Thank you very much again, Gian. Congratulations on a very nice thesis. Good luck for the publication. Looking forward to see the full data set and how this develops. Thank you very much.
Thank you.
Thank you, Carsten. Now I call Dr. João dos Anjos. Hello, João.
Hi. I have no questions. I think that
you can open your camera if you want.
Okay. I would like just to congratulate Gian and MINERVA for these important results, and look forward for the cross-section calculation. I know that this we will have not now, but I look forward for this. And just to congratulate for the thesis that I like it very much. Okay. Just
Thank you.
Not to make any question.
Thank you, João. So, does any of the committee members want to say anything else?
There was in the thesis some picture of the beam structure in page whatever. Let me see. So that would answer Carsten's question. Page 34. I don't know if that's what he's
page or a slide. Page,
no,
right?
in the thesis, page 34 in the thesis, there is the beam structure in time. That could answer some of the. I don't know if he looked at that.
Oh yes, so this is the evolution of how we take the data in time.
Yeah, because that shows very well how the beam, because it's not a continuous beam, that's still beam. So you have during a time you have beam, and during times you don't have beam. So.
Yeah, but I think that Carsten wants to have the profile with geometric in X and Y.
Yeah.
Ah, okay. That's good.
Okay, any other comments, questions?
Just what is the expectation time for the final results about the thesis? That is a few months, 1 year. What is the expectation from MINERVA?
So I am going to keep working on the analysis, and maybe I could say at least, well, maybe 6 months or less, yes.
Okay, and you will stay at Fermilab or will come back to Rio?
I will stay at Fermilab a couple of months, and then I'm going back to Peru.
Okay.
Okay. Okay, I don't have much to say except that it has been a long time since I first met Gian 60 years ago when he started CBPF. He has gone a long way after that. He made a very good work for his master thesis, also at MINERVA. And in all these 60 years, they have been working hard, and they has been very dedicated. And he got the respect from the whole collaboration, and they end up doing this very important to work for the collaboration. Unfortunately, as usual, it's our problem. We don't have much time. We have a time constraint. So his fellowship was over a few months ago. And so, unfortunately, we don't have 6 or 7 years or so to complete the work. So we have to present a thesis with the things we have, although we know that a few more months, 3, 4, 6 months could end up with a much better result. And some of the questions that were brought up by the committee would have been answered, not exist. But unfortunately, we don't have this time. We're constrained to, basically, he has maybe at the best 3 years to do everything, what seems not enough. But anyway, he did very well, has been a very dedicated student. And Gian, do you have your immediate plans for the future, like a postdoc, supposing that the thesis is approved?
Yes, I am applying for jobs now, and I hope to get a job before at the end of the analysis, or maybe a little bit before, but anyway, yes, that's what I'm doing now.
Okay. Can you make any comments about your participation in MINERVA at all, a part of your thesis?
Well,
how was your experience? How was your experience working at a high energy physics experiment? What were your expectations 6 years ago when you showed up in my office, and how you feel now?
So the expectations were very different. So coming to work with people that are directly involved with the experiment is a very nice experience, and also it's very enrichable. It's very I learn a lot, and I continue learning. The experience has been great. Hello, can you hear me?
Yeah.
Okay, we are happy. So the committee now has to convene privately unless someone else has something to say. Ricardo? Ricardo is our secretary. I have to talk to him in português. Ricardo, nós estamos prontos para reunirmos privadamente.
Ok, muito obrigado aí pela participação. Vou pegar vocês todos agora para essa sala secreta, onde vocês vão deliberar, e assim que vocês terminarem lá a conversa, vocês saem dessa sala e voltam para essa aqui, ok?
Como é que a gente faz essa volta?
É fácil, é só sair dessa outra sala simultânea, entendeu? Eu vou pegar... Aí, automaticamente, vocês entram nessa de volta. Jean,
So we don't have to do anything, just explain this. We don't have to do anything. You are going to migrate us to the other room, and then when we are done, we come back to this room. Ok.
That's
Vai
okay?
frente.
Jean, eu poderia que você depois, assim que a gente migrar esse pessoal para outra sala, você descompartilhasse a tua tela, que eu vou compartilhar uma tela aqui, tá ok?
Tá, eu vou deixar de compartilhar.
Ok. Vê se vocês chegaram aí.
Eu fico aqui, né?
Você fica aí.
Tá.
Okay, there is now a sign to about go to another room. For those who do not understand Portuguese, go to the one to the right, or whatever shows it.
Hélio e Jansos, falta entrar vocês. Ana. Ana. Ana, faltou você. Ok.
¿Qué tal, Pessoal?
Alô, Ricardo, você pode me ouvir?
Estou te ouvindo.
Desculpa, eu acho que então eu vou aguardar. Eu acho que elas estão reunidas, né?
Exatamente. Aguarda aí, tá?
Tá, eu vou para o banheiro, volto. Eu acho que levará aqui 5 minutos.
Pode sair da tua tela.
Tá. Obrigado.
E aí, Jean?
Alô?
Estão demorando, né?
Sei. Mas eu acho que é normal.
Tranquilo. Eu só estou querendo saber se você está me ouvindo mesmo.
Tá. Eu estou te ouvindo.
Beleza.
We're back.
It worked.
I'll be back.
Deu tudo certo,
Bom.
gente?
Deu certo.
Tá tudo certo. Ok. Podemos voltar? Podemos falar?
Claro, está todo mundo aí já.
Okay. So, Jean, the committee has convened. The general impression about your work was very positive, consider all very good work. And yes, your thesis is approved, so you can present yourself as Dr. Jean Cáceres and buy a stethoscope for you. Okay. So before, now I want to call you all for a toast. Okay. I'm going to have a toast here, a virtual toast for me. It's a pity that you cannot
you can
have.
drop it here.
Okay, my toast is here. Okay. And congratulations, Jan. And I want to thank all the members from the committee for accepting and for the contributions you have done. And Ricardo, Ricardo, você tira a foto da gente?
Não, alguém faz uma captura de tela aí que eu não consigo, por favor.
Mas então, peraí, quem é que pode fazer a captura de tela? Who can capture the screen?
Qualquer pessoa, né?
Anyone.
Don't know how to do it. Jean, Cássio, Roger, you cannot see Roger.
I can do it. I can do
He
it.
does not have a cam.
Fez?
Já fez?
Então, gente, olha só, tá tudo certo aí, né? Deu tudo certo. Eu, em nome da COEDU, gostaria de agradecer a presença de todos vocês pela participação, desejar um breve retorno às nossas atividades presenciais, todos devidamente vacinados, se Deus quiser. Um Feliz Natal para todos, um bom Ano Novo.
Feliz Natal.
Muita cerveja para comemorar. Se cuidem. E é isso aí. Vou derrubar todo mundo agora.
Ok, thank you.
A Beth só um minutinho. A Beth vai encaminhar a ata para vocês assinarem digitalmente. Ela vai explicar tudo isso no e-mail que ela vai encaminhar para vocês. Ela vai mandar para o Hélio, o Hélio depois você devolve para ela, enfim. Ela vai explicar tudo isso lá na ata da ata da defesa. Jean, vou deixar claro aqui uma coisa que é importante, é a questão do diploma. Os diplomas do CBPF são emitidos no CBPF, mas eles são registrados na UFRJ, que é a instituição vinculada ao Ministério da Educação, responsável no Estado do Rio de Janeiro de registrar os diplomas realizados aqui no Estado do Rio de Janeiro. Como eles estão em trabalho remoto, nossos diplomas estão parados lá desde março. Então, é impossível qualquer cobrança com relação ao diploma no momento. Certo?
Tá.
A gente pode fazer uma declaração de que você defendeu sua tese, tarará, blá, 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 mas a questão do diploma, a gente está nessa dependência da UFRJ voltar ao trabalho presencial. Ok, gente?
Okay,
Yeah.
so to finish, so tomorrow, maybe tomorrow or even today, our secretary is going to send an email with the minutes of this defense for us to sign and return. And Ricardo was explaining that because of this COVID situation, it may take some time for Jean to get a diploma, but he'll get a certificate from CBPF that he can use. So that's all. I have nothing else to say. Thank you very much. You can kick us off. Pode nos jogar fora, Ricardo.
Thank you very much to everybody.
Tchau,
bye bye.
pessoal.
Bye.
Feliz Natal, hein?
Feliz Natal.
Feliz Natal também.
Ana, adorei te ver de novo.
Eu também.
Merry Christmas,
Tchau,
everybody. Ciao, ciao.
Tchau, Ana
Valeu,
Amélia.
gente.
João.
Tchau.
Tchau.
Tchau, João.
Felicitaciones, Jan.